start the session on routing. I have three speakers, Shishio, Geoff, and Geoff. All three speakers are here. You can't hear me? Okay. Maybe get it. How about now? Now. Okay, I have to be really close to this microphone. So yes, welcome back, or well, welcome to the routing session. And earlier I was talking about lunch, but let's leave that here. And we have three speakers and three presentations, and I'm trying to get their titles up here. We have Shishio from Cisco Systems Japan, presenting on BGP Flowspec, case study and discussion, going first. So Shishio, can you get in here? And then we'll have Geoff Snijders from NTT Communications after that, followed by Geoff. We'll do the usual stuff, Q&A after each speaker. When you go up to the mic, please state your name and your company. This session is being broadcast live and will be recorded and then available online later. I think you've been here for long enough that other housekeeping is not necessary. You know where the stairs are, you know where the bathrooms are. So we'll get started. Shishio, thank you.
Thank you.
You can take the mic out.
Okay. Okay. Thank you.
Oh yeah.
Okay. My name is Shishio Tsuchiya, consulting systems engineer of Cisco Systems Japan. This is today's my presentation title, BGP Flowspec, RFC 5575, case study and discussion. This is the agenda of today's presentation. At first, I will quickly explain the BGP Flowspec. After that, I will show the BGP Flowspec case study from a global conference and Japanese operators' opinion. And I did this presentation on January 35, and we did a lot of discussion. So I will share the January certified Q&A information to the participant. This is the DDoS. This is a digital attack map, which is provided by the Google and Albert. And if you are interested in this, please click this URL. And you can find DDoS traffic always changing source, destination, and volume, and patterns, and so on. So, effect of DDoS attack, and this is target services, and the source is variable, and then the DDoS attack will start it. Then customer aggregation node and line and boundwise over backbone and customer line node service will be affected. And finally, target service will be down. So the effect will be all over network wide. So operator is sometimes use RTBH, remote triggered black hole filtering. And this is configured static route to null as a black hole. If in this instance happen, then the BGP advertises the route. Then the DDoS traffic will be stopped. So is it enough to? Is it enough? then why BGP Flowspec will be needed. Non-DDoS user also would be, if operator uses RTBH, then the non-DDoS user also would be stopped. And it is difficult to discover and attempt rule against today's DDoS attack, which is rapidly changing and increasing. So BGP Flowspec using NetFlow to identify DDoS attack and to use BGP attribute to apply the filtering rule in network-wide. BGP Flowspec defined in the RFC 5575 and IPv6 BGP Flowspec in this internet draft. Flow type to identify traffic and action rule to execute policy against the traffic. Both of traffic type and action rule will be advertised by the BGP update. So BGP router use NetFlow to collect traffic information. Then if a NetFlow collector detects attack, then the flow rule and action will be distributed by the BGP. And this is drop rule like ACL. This is polyester to the 100 kbps. This is marking down to the DHCP0. Next is BGP Flowspec case study. I will show the 3 case study from a global conference, and 2 case study from Japanese network operators' opinions. Use case 1 is Time Warner Telecom, which is well-known case study, I think, and which is presented on the Nanog 35 in 2006. This problem is very similar with I already explained, and their OPEX is increasing to the protected DDoS. And their DDoS analysis is a large DDoS attack by a botnet army and script kitty and the TCP front greater than the 1 million PPS, and sometimes since the UDP fragment, and most of attack source from APNIC IP sockets like China, and it is very difficult to track due to the national Great Firewall. They are deployed Flowspec from peer router and transit router. They advertise BGP Flowspec from a route reflector. And they are deployed mitigation from an egress point to the cleaning VRF. What was missing in this deployment? Multi-vendor support they are deployed Juniper and Arbor, and inter-carrier support. They are deployed only intra-areas. And matching the SCP, I think it is a software issue. Use case number 2 is Neo Telecom, which is presented by on the FRNOV 80 in 2011. They are compared RTBH, PBR, and Flowspec. RTBH is a website can protect from a DDoS attack, but no more traffic on website. And PBR can control traffic by hardware, but need a contract to the service provider operator to run and remove the policy when the DDoS are detected. So Flowspec is make static PBR to the dynamic and propagate PBR rule. They don't need any additional communication channel. It is only needed BGP sessions. So they are deployed Flowspec on transit router. They'd like to use on eBGP as architecture, but they cannot trust customer, and they don't like to use flow for eBGP sessions for stability reason. What was next? What was their challenge? IPv6 and VPN-v6 support and traffic monitoring and more vendor. Only BGP Flowspec only support Juniper and Alcatel at that time. Number 3 is GRNet, Greek Research and Technology Network from TNC 2012. I think this is a very interesting use case. Background is mostly similar, and DDoS traffic is increasing by the AMP attack, DNS AMP attack. So they deployed Fire Circle, which is network-wide firewall service. They provided web-based UI to define the policy from the customer, and the message changed to apply the XML configuration to the BGP Flowspec router via netconf. And the eBGP Flowspec propagate policy to the GRNet routers. And they are already deployed this system, and they are expanding the service to the GE and community. If you are interested in this use case, please click this URL. This is not a use case, but this is Alba's Atlas DDoS trend report, which is presented by the Toyo Technica in the January 35. And this is a Japanese trend. NTP AMP is decreasing in Q3 in last year, and attack duration is 92% DDoS, stop within the 1 hour. And NTP AMP attack is decreasing, but other protocols, AMP attack is increasing. This is trend over current DDoS attack. And this is the Flowspec use case number 1 from Japanese operators. He is ISP who is interested in BGP Flowspec. Their AMP attack are increasing under the 5% to the over the 70% over whole of DDoS attack. And variable source 53, this 0, source 123, and source 1900, this 80. They are already deployed some DDoS protection method, RTBH for rapid action, ACL for permanent action, mitigation for premium user service. But if Flowspec will be deployed, some point will be improved. Next is Flowspec use case number 2 from a Japanese operator, who is ISP, who already deployed by BGP Flowspec by the Juniper, and they'd like to deploy that to be more widely with Cisco and Juniper. Flowspec is a very useful feature against today's DDoS attack, but one considering point is scalability spec for a forwarding router. They had trouble, rule was too long, so forwarding router could not apply the filter, and as a result, they stopped the, not only DDoS, but also a normal traffic down. Next is January 35, the Q&A. January had a session over BGP Flowspec in the January 35. The presenter is myself, and Hirasa-san, who is a engineer of BigGlobe, and Agatsuma-san, Toyo Technical. Toyo Technical is a partner of Arbor. They explained somewhere about the traffic trend report. So I'd like to share the question and the discussion on January 35 meeting to the participants. So this is a very simple question. Does BGP Flowspec really useful? So I did confirm it in detail for RFC and IETF working group draft. Flow type has operator code which can specify less than and greater than and equal. So I think it is very useful for the operators. And we also check type of action rule. Most of the action rule is already defined, both IPv4 and IP. But please check redirect IP. I think this is a little bit confusing because they have two internet drafts, and one is quite old, and another is a new one. But both over type code is different. So we should watch IDR working group activity in this redirect IPv4 and IPv6 address. And this is the implementation status. Finally, Cisco supported BGP Flowspec, both iOS XR and iOS XE. And Juniper, Alcatel, and Arbor already supported BGP Flowspec. And Genie Networks is a NetFlow collector supported BGP Flowspec. And Extra BGP already supported BGP Flowspec. But how about the interoperability in multi-vendor? As I already explained, there is some interop report, but I think may need more interop tests to deploy the ISP network in the network wide. This is a question from IXP operator. Flow is real enough to monitor ISP traffic. So Agatsuma-san is who is Toyo Technical explained different point of inline type and off-ramp model. Today's DDoS attack is DDoS volume is very high, so off-ramp solution would be reasonable. How is DDoS on mobile network? Today's most of mobile carrier deployed carrier-grade NAT as a short-term solution over IPv4 exhaustion problem in Japan. And malware DDoS tool over Android already exists. Flow-based filtering will be more important to reduce side effects over DDoS. And the performance issue, it is completely depend on the router's architecture. Usually, current router using TCAM, if they'd like to execute QoS and PBR. So, performance impact would be minimized. eBGP use case, Flowspec should work in the eBGP peer, but eBGP validation rule for a receive route should be relaxed. On transit AS and router server on the IXP, it would be desirable services, because if one AS send a DDoS, then they affect another AS. And this is just idea. Validation rule should be relaxed, so maybe we should consider the coexist solution with RPKI to be a more powerful security solution. It is just an idea. And we should check a revised validation procedure for BGP Flowspec. This is internet draft. And how is OpenFlow DDoS solution? This question from some vendor and some researcher. And there is the OpenFlow DDoS protection solution. So, and as I already mentioned, some router execute PBR by TCAM. And also, hybrid OpenFlow use TCAM. So, I think different point network architecture, full distributed VS controller, and API, which means programming filtering rule. OpenFlow, one orb use OpenFlow as a programming rule, and another is BGP as a program, as a API. This is summary. Current DDoS high volume, short duration, AMP attack variable, and increasing. BGP Flowspec is a useful solution against today's DDoS attack. BGP Flowspec is almost ready to deploy in the ISP network, but I think we need a detailed implementation information over each of vendors, like scalability, next hop address, and IPv6 support. And I think we need an interoperability test result. And eBGP should work, and the customer may desire on-demand firewall PBR service, like a Fire Circle, Okay, my presentation is ended. Any question or comment?
No questions? Okay, thank you very much.
Thank you very much.
Next is Geoff Snijders from NTT about selective blackholing and how they used it in NTT.
Thank you for attending this session. It is quite an honor to be amongst the smartest and brightest of the Asian technical community. I want to talk to you today about selective blackholing. By the way, I'm Geoff Snijders. I work for NTT Communications, where I analyze the current state and future direction of its global IP network. And you can reach me through Twitter or email should you have any questions after this presentation. In this presentation, I'll cover what selective blackholing is, and more importantly, how you as a carrier could implement it and offer it to your own customers, or if you're a customer of one of the networks that supports selective blackholing, how you could use it to control the damage that DDoS attacks inflict upon your network. The trick with selective blackholing is that you start discarding packets when certain conditions are met. And these conditions, the way I implemented it in this presentation, are of geographical nature. In other words, if packets enter the network at some point, for instance, on a different continent than where the prefixes originated, with selective blackholing, you could, for instance, drop those packets. Or if the packets come from outside the country, then the geographical conditions are met if the end user signals with the BGP community drop packets from outside the country, then you can do that. Why is this approach important? Most content hosters will host the content relatively close to the eyeballs that consume the content. For instance, if you cater to the Japanese market and you provide game servers, you will not host the game servers on the other side of the world. You will host the game servers in Japan. So one could say that the larger the distance is between where the prefix is originated and where the consumer of the content is, the less important that type of traffic becomes. Or simplified, a Japanese web shop owner will care most about Japanese eyeballs and less about European eyeballs when he is under attack. In other words, the scope of origination and where you start discarding is very important. If we compare this with classic blackholing, for instance, in NTT's network, it's 2914:666, and I believe many of you have implemented similar schemes. The big issue with classic blackholing is that it's an all or nothing proposition, where you indeed stop the DDoS attack and prevent your uplinks from congesting, but at the same time, the victim IP address is no longer reachable, and it stops generating revenue if it's, for instance, a game server or a web shop. And I feel that we as internet operators should have more choices in that space. Therefore, there is now selective blackholing. There are two tricks or aspects that you should keep in mind with regards to selective blackholing. I would not consider selective blackholing DDoS mitigation, because there is no scrubbing, there is no smart stuff. It's either packets get dropped or they get forwarded. On the other side, this is a very cheap method. It's much cheaper than using scrubbing devices to clean the traffic. It's a different product than normal mitigation. The first assertion that we should keep in mind is that it's better to at least remain partially reachable during an attack than no reachability at all. Like with the 666 black hole community, there is no reachability at all. With this community, there is partial reachability. Another aspect of this morphology is that even though you signal to your transit provider's network that you do not wish to receive packets from, say, outside Asia or outside Japan, chances are, and it depends on the routing policy of your providers, peers, or customers, that still some DDoS traffic slips through. We know that with the DDoS amplifiers, the NTP boxes, the DNS boxes, that they are distributed amongst the whole world. They are hosted everywhere. So this means that even though you use selective blackholing, still some traffic will pass through. But hopefully it's small enough that you can still sustain this on your uplinks. Now, let's take a look at what selective blackholing actually means when we do some measurements. I have used RIPE NCC's beautiful Atlas system. RIPE NCC has distributed thousands of probes across the whole planet, and you can run from those nodes. And in this example, I am originating a IP address, a /32, to which I associated a BGP community that triggers black hole outside a radius of 1,000 kilometers. And what we can see on this map, that for instance, North America, all the probes are colored white, and that means the probes cannot reach the destination IP address that I flagged with the selective black hole. And we can see that inside Europe, closer and closer to Amsterdam, more and more probes can actually reach the destination IP. So if we translate this to the earlier case, if you're a Dutch web shop owner and you sell wooden clocks to Dutch people, you can still cater to most of them, but you don't get amplified DDoS traffic originating from, say, Asia and North America. A different style of community is that instead of a geographical distance, you say discard packets that come from outside the Netherlands. And there's one very noteworthy thing in this measurement. On the east side of Africa, you can see a few red dots. Those are Atlas probes that still could reach the destination IP address. And this is because of what I call the disease of the routing table, remote peering, where people connect over such vast distances and peer with each other that the actual topology and the perceived topology no longer align with each other. So this is one of the weaker parts of selective blackholing. It kind of depends on networks using, for instance, hot potato routing and interconnecting with each other in places which are logical. We go back to discards outside the Netherlands. I've now run a measurement where I test reachability inside the Netherlands, and you can see that all of the probes are green, and there is near 100% reachability of the IP address that was under attack. But enough about the Netherlands. I've done some measurements for an IP address that was originated in Japan, on which the community was associated to discard packets coming from outside Japan. And we can see that within Japan, reachability is quite good. It's better than classic blackholing, where there is no reachability. And outside Japan, many probes can no longer reach the victim IP address. So this should visualize a little bit what you can expect from selective black holes in terms of reachability. Now the fun part, how do you set this up as a carrier to offer this to your customers? In this specific implementation, we will try and implement 4 different carriers. One is black hole outside this country, where the country is the country in which the customer connects with you. Outside this continent, outside a 1,000-kilometer radius, and outside a 2,500-kilometer radius. The distance-based communities are not useful in all contexts, but for instance in the Netherlands there's quite some linguistical overlap between, for instance, Belgium and the Netherlands and Luxembourg. So instead of flagging we need this outside the Netherlands, it needs to be discarded, you might want a slightly bigger range because there are still potential revenue generating eyeballs that want to reach your IP address. Distance is measured with an Haversine calculation from router to router. So it's not the actual fiber paths, it's just you take the GPS coordinates of routers and calculate the, as they call it in English, how the crow flies. So the direct shortest distance. The first thing you need to do, and this is crucial to implementing selective blackholing, is that you assign integers to each of your devices. So every router, on the left column we have tki.jp, which could be a routing device in Tokyo, Japan. We've assigned to the Asian continent number 3. As for the country code, I use the ISO 31661 specification, so I don't have to invent numbers myself, but can just use an existing database. For each city, you could also assign integers to your routers. And last but not least, the actual GPS coordinates of the device. And you must assign numbers to every routing device in your network to make a scheme like this work. These numbers we configure on the devices to make them community lists on which we can match in our routing policies. In this presentation, I'm using as an example brocade configuration, because if you can configure this on a brocade, you can configure it on anything. If we look at the top router, our New York router, we've assigned the number 26 to represent the New York metro area, 840 is the ISO-defined number for North America, and 1000, the 1 from that number represents North America. And we do this for each and every router in our network. And you'll notice that if you compare the configs from router to router, the only thing that differs between those devices are these community lists. The rest of the policy can be cookie stamped and just copy-pasted from device to device. Before we dive into the route maps, I'd like to highlight and imprint a little bit what happens where. Let's see. On the far right, there is Mr. Snijders, who announces a /32 tagged with community 15562:664, which means black hole outside a 1,000-kilometer radius in this example. And the customer announces this to the edge router of the provider. The edge router inside the provider's network will add communities to that prefix to sort of enrich the metadata to indicate the geographical scope. So the customer only supplies the desired action, and the service provider will then add additional information. So later on in the network, there can be tested whether the routers are inside the scope or outside the scope. The prefix propagates through the network. It reaches a Paris router. The Paris router can check whether it's within the 1,000-kilometer scope or outside the 1,000-kilometer scope. The Paris router will receive both DDoS traffic as well as legitimate traffic. The prefix propagates further, crosses the transatlantic sea, arrives at a router in New York. Clearly, New York is more than 1,000 kilometers away from Amsterdam. And the trick on the New York router is that it installs a discard route in its FIP rather than a forwarding route. A crucial aspect of selective blackholing is that on inbound, on your IBGP policy maps, you verify two important things. If we take this as an example, the IP address 10.0.0.1 is used as the next hop to make packets disappear into the bucket. The first stanza of our inbound IBGP policy is classic blackholing. If community 666 is associated with the prefix, we will just install a discarding next hop. In blue, you can see match community 660, 662, 664. Those are the selective black holes that we, communities that we expose or communicate to end users as communities they can use to trigger the desired discarding behavior. If the prefix carries one of these selective black hole communities, we jump towards a different portion of the routing policy where we will figure out what to do exactly. But if on the IBGP received prefix there is no such community, we will match with permit 1000, which is the accept anything clause, because you want to accept anything on IBGP sessions. So we jump over the accept anything to a portion of the route map where you see match community, this metro, this country, or this continent. And we need only those three matches to create very advanced routing policies. Because if the prefix matches with any of these, it means that the edge router on which this policy is applied is inside the region. And the stanza here at 1100 is just permit. So we install the /32 that the customer is announcing to us in our forwarding information base as a forwarding route, and packets will just follow their normal path, and it will be as if no black hole community was applied whatsoever. However, if it could not match the prefix with any of these communities, then we end up at 1101, and that stanza installs a discarding next hop. So on IBGP inbound, the check is really, am I inside the region? Is the action to black hole outside the region? If I'm inside the region, I must forward traffic and not install a discard route. If I'm outside the region, I will install a discard route. So that's the IBGP side. Now let's take a look at the customer-facing side. The first stanza in red is the regular 666 style of blackholing. You just verify whether the customer is allowed to announce a prefix. If it contains the 666 community, we set the next hop to our discard IP address. We add no export because we don't want to export these /32s to our peers or other customers. End of story. However, at stanza 300, permit 300, we again validate whether the customer is allowed to announce these prefixes. We verify whether one of the selective black holes is associated with the prefix, so the 660, 664, one of those. And if that is true, we jump to a different portion of the routing policy where we will figure out what needs to happen next. Then the third one is just a regular IP transit service you offer to your customers. We verify whether they are allowed to announce the prefix, and if they're allowed to announce the prefix, we will just accept it in our network, and that's business as usual. At line 13, there's a deny any clause, because if the customer is announcing something that is not in their prefix whitelist, then we will ignore the route update, and that's it. So remember that we were jumping towards stanza 600. We validated that a selective black hole was requested, but at this point in the policy, we don't know yet which action exactly was requested. First, we match the exact surface, so in this case, a black hole outside a 1,000-kilometer radius, and then we add a community to accomplish that style of propagation. Second stanza is 2,500 kilometers, and we add different communities which will trigger the intended behavior later on in the network in those IBGP route maps. Then there is discard outside this country. Yet again, a different community is added to enrich the prefix with the metadata required. And we have discard outside this continent. And the smart observer might recognize that 840, we earlier assigned 840 to represent the United States. And we declared that 1,000 is North America. So these communities are very easy to figure out that if somebody is connected in North America, then this stanza generated for the customer must have 1,000 added when you want to accomplish blackholing outside of the continent. Same for the country. We know upfront which values should go there. So this is again the overview. We just learned that on the far side of the network, the edge that connects with the customer, there we add specific communities to identify what should happen where, and we honor those requested actions on every IBGP inbound policy. However, how did we figure out how to do the 1,000-kilometer and 2,500-kilometer based communities? Because how do you predict what these communities should be to get the distance-based blackholing in it? I wrote a very small Python script that, based on the small database that we defined on the beginning of the presentation, will calculate for you which communities are required to accomplish the intended goal. Because routers obviously are not aware where on the planet they are located. They have no location awareness, but we can fool our routing policy into making it appear as if they do know this. So if you download this Python script and you run it, it will output per device which additional communities need to be added to the prefix to accomplish an or outside 2,500 kilometer radius. The software is freely available, so if you're interested, go ahead. And the trick, if you look at 1,000 kilometers or 2,500 kilometers, is that if you combine the country, metro, or region-specific communities, you can group routers into smaller subsets that are representative of any router within the 1,000 or 2,500 kilometer radius. So for instance, we could generate that community 2000. It covers Amsterdam, London, Stockholm, and New York. This table is not complete. The Python script will iterate through every possible option, and only if the option satisfies our needs, it will output some data. But you might get the gist of this. When deploying selective blackholing, there are a few recommendations that I have for you. First of all, automate everything. If you try and maintain a routing policy by hand that is as advanced as selective blackholing, you will sooner or later end up in tears, because it's quite hard for humans to keep everything aligned and properly configured. So use some scripts to generate your configs and automatically configure your routers rather than doing this manually. You can use your existing CMDB or create a new one in which you store those integers that we covered at the beginning of the session, where countries are assigned numbers and the countries are associated with routers, where we input the GPS coordinates. Stuff like that is necessary to generate the routing policy required. A very neat thing about selective blackholing is that although it's quite an advanced feature, configuration-wise, you don't need that many lines. You saw the IBGP in policy. It's just, another 20 lines that you add to your IBGP inbound policy, and suddenly your network can do all these crazy things. And I mentioned earlier that per router, the config is almost exactly the same, aside from the community mappings to which you can match in the policy. And by deploying this on Brocade, Compass, Juniper, Cisco, iOS, and XR so far, I have proven that you can deploy this on any network equipment that exists. So this is a very cheap way, without investing in additional boxes or additional hardware, to recycle your modern or maybe older hardware to do things that benefit your customers. Customers might not ask for this today because most customers don't realize that this could be a real thing, that it exists. And that might be a chicken-egg problem if you try to justify this internally, and one of your managers tells you, well, we've never had a feature request from a customer where they would like us to drop traffic that comes from outside the continent. And you should reply, well, it's because they don't know it exists. And last but not least, it saves both the service provider and the customer money. If the customer signals to us that they don't need traffic coming from Asia or from Europe, then we don't have to transport the DDoS across the Pacific and across the transatlantic oceans. We can drop it on the floor as soon as it enters our network. And that's a huge money saver right there, because nothing is as annoying as transporting 100 or 200 gigabit DDoS and then try and squeeze it through a 100 megabit port to the customer. You drop the packets on the floor, but it still took space and time on your backbone. So for both parties involved, there is a win. If we look at NTT, roughly a week ago, selective blackholing was implemented in our network, and it's now available to all customers that have blackholing services enabled. So aside from the regular 666 community, we now offer black hole outside the region. A region is roughly the same as a continent in our network topology. And we offer 664, black hole outside the country. So it will depend on where you interconnect and the size of the DDoS, which of the two makes most sense for you. And for DNS anycasters, we have an inverse where you only black hole inside a specific region or inside a specific continent. So the services where you interconnect on various different countries or continents with NTT can remain running as is. My personal recommendation is to, if you have scripts that inject 666 black holes today, replace the 666 portion with 660, because my measurements show that in most cases, black holing outside already greatly reduces the attack traffic you receive. From a customer perspective, there is one thing I should mention. When you use a 666 community, you usually discard the packets inside your network, and that discard route you use to generate the /32 announcement to announce it to the upstreams, to the transit provider. So previously, you might set a static on a Juniper like this. In this case, we try and black hole an IPv6 address. We install it as discard, and we add a community to trigger the behavior in our upstreams network. But with selective blackholing, where the requested action is to black hole outside a region, that means that you should not black hole the traffic yourself inside your own network. So instead of using discards in your own network, you could do a trick on Junos like no install. So that means that you still generate the route and you can still announce it on eBGP, but you're not installing it as a discard route in your own network. Because it'd be a shame if there's all this traffic that comes from within the region, and the moment it hits your network border, you throw it away. So I recommend if you start using selective blackholing, do some test runs, maybe use RIPE Atlas to validate whether what you're trying to accomplish is actually accomplished. Now we're at the end of my presentation. This is a picture of my cat for your amusement. Do you have questions so far? I realize I've said a ton of things in a relatively brief time period, so if you want to get back to me later and ask questions.
All questions at one and answer, or you want to do one and then?
Sorry?
You want to take all the questions and answer at once, or you want to do one question at a time?
One by one.
Okay. We have 5 minutes
Hi.
for him, so.
Okay. It's a short question. I'm Leo.
Can you identify yourself and your company, please?
Yeah, I come from China Telecom. Yeah. So I think this idea is quite a brilliant idea. It can prevent a lot of DDoS attack very effectively and low cost. Almost no cost, actually.
Smart observation.
Yeah, it's a very good idea. So I wonder, how many time did you spend to deploy the policy on the whole network?
I've implemented selective blackholing twice. At the first employer, it took me 2 weeks full-time, and I was then working 70 hours a week because I was very excited. And the second time took slightly longer. This was at NTT. Because NTT has multiple vendors, so instead of doing the implementation once, I had to basically do it 4 times and test 4 times for all the vendors that we use. But all in all, if you aggregate the time, I'd say it was between 6 and 7 weeks. No, at NTT I was supported by a big team of people that were kind enough to help me figure out how to do this. Aaron.
Hi, Aaron Hughes. Aaron Hughes, 6 Connect. It seems to me that this is a overly complicated, and I'm wondering why you don't use something like metric, where you can just add a value at a given link crossing a boundary and match a range to figure out distance, rather than have to do all the calculations for cities. In other words, at every time you cross a border, just add some arbitrary value to metric, so that distance is, a metric of plus X for a distance, and then you never have to know the actual distance because you can figure it out from the origin.
Your suggestion is valid. However, this implementation was done on stuff like Cisco iOS and Brocade, and it's much harder in those route maps to add metrics like you suggest. So if this were a Juniper-only network, I could see your solution as being an alternative approach to accomplish the same.
Yeah, so Cisco as well, just set metric plus X. Just when if people are looking at implementing this, it seems to me that that's the most logical thing, is just to start with a given metric for all customer prefixes, and every time you cross a border, add some value, whatever it is, 5, 10, 15, and then you can always match a range to figure out distance rather than having to map this whole thing out.
It's an interesting approach. Thank you for sharing it.
Yes, of course.
Sorry, Dorian Kim, NTT. Just one of the things that you have to consider when you deploy anything is that you have to consider the existing deployed base. Then the deployed base also includes the structure of the routing policy. So in this particular type of case, it just made sense for us to slot this into an existing framework of the routing policy that way.
Hey, Job, it's George from APNIC. You've got 2-byte ASs, which means you can use community strings because a community string is a 32-bit number split into a 2-byte and a 2-byte component. How do we do this with 4-byte ASs?
4-byte ASs. I personally, if you want to be a carrier and offer transit services to customers, you should go to your RAR and get a 2-byte ASN. Because realistically today, it's very hard to run a carrier network where you expose communities to your customers and you have to tell them, well, there's 0 bytes available for locally significant information. If you do not have plans to ever provide transit services, 4-byte just works great. But it is a valid point. So the cheapest way is to renumber to 2-byte or use private ASNs and risk maybe conflict with internal policies that your customer has. Are there more questions?
No questions for Job. Thank you very much.
And as I mentioned, feel free to email me if you come up with questions later. I will happily assist you implementing this in your networks.
Next, we have Geoff Huston. And Geoff is going to talk about the securing of the routing system.
Thanks a lot. My name is Geoff Huston. I'm with APNIC. This is kind of a weird session that it was sort of a bunch of things in BGP, and I'm not sure if there's any particular theme in any of these talks. So the first two were basically around DDoS mitigation in various forms. So I must admit.
Microphone volume.
I think it's the height.
It's the height or it's the volume?
It's the height. It's the height. You have
It's
to
the
be
height.
really close. So
Oh, God.
take it in your hand.
I must admit, we have run out of 2-byte ASs. There are none. This is now on. We have run out of 2-byte ASs. You can't reinvent new ones. If you're going to do anything with ASs, you need to accommodate 32 bits. But that's a side comment. This is really an architectural talk rather than a process talk. This is not about basic technology, it's about architecture and design. So if that's kind of dull, leave now, because I don't really want to talk about specifics. What I want to talk about is the design of security systems, in particular in routing. So what you've heard so far is a couple of the many ways that you can be bad on the internet. And you know, it's really easy to do all kinds of things that are really, really bad. You know, everyone port scans all of the time, everyone spams, everyone attacks stuff. It's just the run of the mill. And these days, if you're an ISP and you haven't contracted some really large person to do data scrubbing for you, you'll probably be out of business. Because this is a really, really malicious network these days, and the attack capabilities are well in excess of almost 90% of the ISPs. So it's only other 10% that are large enough to absorb it, and almost no one is able to actually really, really, really deflect it.
Pause you for a minute.
Sure.
There's sitting in the front for those in the back, so feel free to come by and sit in the front. So there's plenty of sits up here, so thank you.
So there's a few hints on how to be naughty. But you know, all of those are kind of means to an end if you really, really, really want to be naughty. It's no good me trying to pervert individual machines and subvert them. If I can rely on all of you working perfectly, all I need to do is attack routing. Because then I can make your machine go to places that I dictate, because that's what attacking routing is all about. So if I was really bad and evil, I'd attack routing. From there, I can play with you. If you're not doing DNSSEC, I can play with your DNS. I can isolate critical resources. I can bring stuff down. Now, don't forget that these days, various nation states treat cybersecurity at the same level as fleets of aircraft or navy. That the amount of investment by nation states in this area, in both attack and defence, is considerable. Because this is critical infrastructure. And because it's critical, it's a point of vulnerability as well as points of attack. So, you know, it's not just the avid 16-year-old with nothing else to do, or the bored computer science student who has nothing to do on a weekend. This is professionals like you and I. So obviously, a lot of this stuff is incredibly vulnerable. And so there's this sort of question, if you're going to attack routing, how can you tell it's being attacked? Well, because the advertisement's a lie, right? And so everyone goes, oh, YouTube, 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 YouTube. We all talk about YouTube. But how do you know an advertisement is a lie? There's one way of doing this, and you actually go back to the regional internet registries, and you know, the name registry was deliberate, and you look at the registry. And you go, if I see a prefix in the routing system that is being advertised and used and reachable, then shouldn't I see it in the registry? Yeah? True? So let's talk about all the routes on the internet today that aren't in the registry. 5.100.241.0/24, announced by a bullshit AS. That didn't work. 23.92.160.0/24, announced by Epson robots, and so on and so forth. Yep. But there's more. And more. And more. And more. And more. Now, the thing is, you know, you guys are professionals. You do this for a living. You're really, really, really good at what you do, aren't you? So that was all the addresses. How about the AS numbers that are used in the routing system that aren't in the registry? AS 1446, announced by Quest. It's a bullshit AS. AS2733 announced by UUNet, bullshit AS. AS3322. I could list them all, but you're getting the point, aren't you? It still goes on. I really got bored at this point, right? And there's more, right? You're really, really good at what you do, aren't you? Because all of this stuff is crap. Oh, and by the way, there's crap in 6. So if you think that we're doing a good job, I don't understand the evidence that got you to that conclusion. Because none of you actually do this basic check of the routes that I carry versus understanding there is some registry somewhere that said that was a real address or a real autonomous system number. You don't check. You just carry this stuff. And you and I could put anything there as long as I was prepared to find any old ISP that took my letter of authority and believed it. Because all we do now is kind of meaningless bilats. So we're doing a lousy job. Mutual and very vague trust models that realistically don't work. No one audits. No one checks this stuff. And we're used to it. That's the normal background radiation of lies. So could you detect if I put in one more route? As long as it wasn't a route about you, you don't care. Or you. As long as it's not your route, who cares? Certainly not you. And that's what goes on. This routing system is just a bunch of institutionalized lies. And we don't care. We don't place any value on actually cleaning it up until you're the victim. And then, of course, it's everybody's problem. I'm the victim. But to be perfectly frank, if you're the victim, it's your problem. No one's going to help you. It's not worth their money. So you've got a really lousy system here. And nobody cares enough about the entire system, and certainly nobody cares about anybody else. So this is a classic problem. And all the black hole technology in the world has a similar issue. You trying to get me to do things to fix your problem won't work until money changes hands. And unfortunately, that's not what's going on. So, quite frankly, we're deep inside a tragedy of the commons. Nobody can singly pull us out. Lowest common denominator test is we just accept institutionalized lies and we have no defense. Wow. Worried yet? You don't seem to be, because no one's fixed this and it's been going on for decades. So, the theory of security. You've all gone to security seminars and tutorials and so on. You should be able to spit this straight back out at me. Nobody but you should be able to change what's in your router. Your router, not my router. As soon as it's my router, I own you. So you've got to protect your router. I shouldn't be able to change the config in your router. So, all the standard stuff, secure your router, SSH, blah, 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 blah. This is just standard stuff. If you're not doing that, don't be an ISP. You're too much of a risk to everyone else. So the first thing is protect your routers. The second thing is you really, really should do basic routing sanity checks. Because when you start doing things like multipath eBGP, man-in-the-middle attacks are just another step away, right? So if you're going to do that kind of technique, use basic integrity across that channel. So all of those usual practices, TCP, MD5 checks and so on, you should be doing passwords across exchanges, etc. Because if you don't, I can inject myself inside your session, I can behave like the other person and give you bad information that you can't tell. But again, I haven't told you anything you don't know. And if that was news to you, get worried and start reading, because this is all standard stuff. This is nothing terribly rocket sciencey. The next one, though, is a lot harder. Because the next one is somebody out there takes over a router, not yours, and injects bad information. How do you tell good from bad? It's just a BGP update feed. AS666 has managed to be taken over. It's injecting a bogus route for 10.0.1.0/24. And you know, just to be even more evil, it sets the no export bit on this. So it says to AS4, I want to capture your traffic, but don't tell anyone else about my attack. Let me just limit this attack to just you. How do you do that? So almost every course you've been to on BGP security, the problem is it didn't tell you how to stop that, because this truly is rocket science. Because routing is rumors. BGP is a rumor mill. I tell you about connectivity that I have. You turn around and tell your neighbours about my connectivity. You then turn around and tell your neighbours and tell your neighbours and tell your neighbours. By the time it gets up to the back of the room, how do you know I said it? How do you know it was all about me? How can you tell if somebody in the middle changed it? You can't. All the other Australians lie. But you know, you see what I'm saying. I can't put that into BGP. You know, this is my route with an Australian accent. So that's the basic problem that we're trying to solve in routing, and it truly is rocket science. How do you tell good from bad in a rumour mill? And that is an incredibly difficult problem. So what do I mean when I say good from bad? There are a bunch of very, very basic questions that need to be understood. I see a routing update, 10.0.1/24. Well, who injected it? Who actually said that this was their prefix? And more to the point, if they're an autonomous system, did the owner of the prefix truly let them advertise that route? Was that, you know, a permission thing, or did they just go, oh, it's a Wednesday, I'll just advertise this route? And last but not least, when I hear that update, what it's telling me is that there exists a forwarding path on the internet for packets that I send to that destination that are going to reach that address. Am I willing to trust it? Is that the real path, or does it go through you because you're evil? How do I tell the difference? So more to the point as well, just to make it even harder, because this really is rocket science, it's got to be done fast, and you're not allowed to spend any money. None. Because no one wants to spend money on security. So it's quick, and it's cheap, and it's secure. It's starting to get impossible. Look at the scale of the problem. Here's our update. I received it a little while ago. That's exactly what's inside BGP. So the first question is that a valid prefix? Wow, tough call. How would I know? And don't tell me who is, because that's not the answer. That's a really tough one. How does my router know that's a valid prefix? Because it doesn't have any kind of RIR database sitting on it. So, okay, straight away there's a problem. How do I know that's a valid prefix? Wow. How do I know that's a valid ASN? Hopefully no one owns that ASN in this room, do they? Maybe they do. It's a real update. I've forgotten who does own it. And the next thing is, did that ASN truly have permission to advertise that prefix? Now, I don't know. I'm living in, you know, somewhere else on 4608. But I'd like to actually understand that. And I would actually like to understand that path, 4608, 1221, 4637, if you're familiar with this stuff, it's me, APNIC, to Telstra, to Reach, to Level 3, to, oh, God knows, somewhere. Yeah, is that a real path? You don't know, I don't know. This is hard. So those three questions, the validity of the AS in the address, the authorization, that AS was truly authorized to originate reachability to that address. And then last but not least, and it's very important, that the string of networks to get there is the right string, and it's not being hijacked by some third-party nasty person who wants to inspect the traffic on the fly. Right? So, what have we done over the last 30 years to try and answer those extremely difficult questions? Who uses who is? One. 2, 3, 4, 5, 6. It's awesome, isn't it? Truly awesome. You know, you put in ASCII crap, it sends back ASCII crap. Parsing it is close to impossible, and don't forget the RIRs, just to be different, every RIR answers in a different format, but it's just ASCII. And of course, it's not a protected channel. So, you know, you send out ASCII stuff into the ether, port whatever it was, 43, and an answer comes back from somebody. Might be a real RIR, might not, it's unprotected. And you go, wow. So that was an approach to validity. Awesome, awesome. The first approach that we kind of got to, and we've used a fair deal, is doing entries in a routing registry. So that's kind of approach 2. The third that came up in a number of research papers and actually keeps on coming back and back again. There's this theory of the internet that goes, it doesn't matter what the question is, the answer is always the DNS, right? And the sort of corollary of that theory is, no matter what you try and do, it looks like the DNS anyway. No matter what you're trying to do, the DNS can answer it. So if you've got a problem about addresses and the DNS, well, it's obviously reverse DNS. That's the answer. So that's answer number 3. And answer number 4 is certification of an allocation registry, which is a long way of saying it's a PKI. Now, all of these have one thing in common. When I say 203.10.60.0 is my address, I'm relying on some other third party to say Geoff's right. So it's kind of a trusted third party attestation. Theoretically, WHOIS comes from a registry. Theoretically, the routing registry is run by someone who knows. Theoretically, the reverse DNS is run by someone who knows what they're doing. Sounds weird, doesn't it? And lastly, you know, certification. It actually, the person who gave that certificate out, that third party, knew what they were doing when they certified me. So all of them rely on some kind of third-party action of varying degrees. None of them are a good fit. So that's really wordy, and possibly because we've had about 20 years of experience with route registries, it's deliberately wordy. But the way route registries work is you say in advance what you think you're going to do. People can use that information to filter what they hear about my routes. And if what they hear doesn't match what I said I was going to do, throw it out. So if someone lies with my addresses, they have to lie within the framework of what I said I was going to do. Okay, lie. I was going to do it anyway. It's kind of, well, you know, so what? So the routing registry is kind of a registry of intent about policy. And it allows other folk to filter about me. So way back at the back of the room, you can look up my policies in a routing registry of AS131072, and you can even construct a filter about that if that's what you want to do. Right? So in theory, that's brilliant. In theory. How many registries exist in the world today? About 50. Well, you know, you have one, you might as well have two. If you have two, you might as well have three. Oh, what the hell, I'll run one too. Are they consistent? No. Are they full of old junk? Yes, because no one ever removes anything, just in case. Are they consistent in their implementation? No. Are they consistent in their language? No. You start to see the problems. That there is no routing registry. There are many routing registries, and quite frankly, the authority models are various. The RIPE NCC routing registry used to accept entries that described any prefix. They didn't check for many years. So you'd look to the routing registry, you'd find attestations about routing for other addresses. That's okay, but people do typos. So the other addresses were maybe my address. It's kind of, I didn't say that. Why are you saying that? What's your authority to say that? And so this whole issue of the route registry is you can't trust it because the admission policies, who can say what, aren't obvious to the user. But there's one more thing about a route registry which is a bit like the awesome power of Whois. It's a non-authenticated secure channel. So you do a query to a route registry, it's just TCP, I can sit there in the middle and hand back anything. The entries aren't signed, anybody can attack it. Not good. Populating reverse DNS, not good. Not good because, quite frankly, the zone delegation management has its problems. And if you think it's easy in V4, no matter what the issue is, say V6 and panic. Because when you start to deal with 128 bits streaming through a reverse registry, things get awfully difficult awfully quickly. And quite frankly, again, if you're going to do this, you need DNSSEC everywhere, private key management. Everyone loves doing private key management, don't they? And are we putting all of our eggs in just one basket? One egg, one basket. Because then DNSSEC becomes the key to the entire internet. Feeling comfortable? And in fact, the root key of the DNS is the root key of the entire internet. Feeling better? Feeling okay yet? One key, everything. That, Lord of the Rings all over again. It's not comfortable. The number PKI has its own issues, There is no tool set we can borrow. You can't use the existing PKI stuff because when you start doing PKIs for addresses and AS numbers, you're into new technology. And quite frankly, none of you guys operate this stuff, so it's all new. And all the secret voodoo handshakes of cryptography just look like wacko nonsense to most of us. Kind of, why are you doing that? What's this HSM stuff? How long do the batteries last? Is it really only 5 years? How do I roll keys? What the hell is going on here? So you guys sort of look at this and go, wow, that is weird stuff. Don't want to do it. Let someone else do it. You manage my private keys for me. What? You manage my private key for me. It's okay. So I can be you, can I? It's okay, Geoff. It's okay. Some of this is pretty weird, right? And of course, the other issue is the distribution of all of those certificates and CRLs that actually underpin it is its own problem. Because if you're trying to secure routing, a distribution protocol, by distributing credentials using routing? Oh yeah, routing. There's a certain circularity going on which, will make anyone's head explode. It's a problem. So, the foundation stone is good. I kind of like a PKI because I kind of like the idea that it's my private key. And as long as I don't give it to you and I keep it a secret in my infrastructure, it really was me. And if I sign something, only I could have signed it. So for God's sake, don't give it to somebody else. It's your private key. It's no one else's. And if you keep that up, you can actually do some decent stuff. You can actually sign route registry entries digitally. So then it doesn't matter where you got it from. It doesn't matter if there's a man in the middle trying to attack the route registry pool. If it's signed, tampering is detectable. You can actually see, I shouldn't trust this. It's been manipulated. I can even do it in the straight up route request. Please route my IP address. I am 203.10.60.0, signed Geoff. Signed with that address. Only I can sign it. Non-repudiatable. It was really me. It's genuine. Or you can put it in BGP, and that gets a bit interesting. So what about BGP? What can we embed into BGP and get away with? So there are two questions in BGP, and they're kind of separable. Was I the right party to originate that address? Question one. Over there in the back of the room, you saw a path to get to me snaking around the room. Is that path trustable? That's a second question. Is the path that I'm being given in BGP the real deal? So, in origination, validity of the address, and is the origination duly authorised? Is the path real? We've had two approaches to origination, and one of them is kind of this issue of managed filters. If you've looked inside this sort of RPKI framework, you see the RPKI router protocol. And what it's trying to do is to say, routers really were built 20 years ago and they've got no power whatsoever and they can't do crypto. So instead we'll do a dedicated box doing crypto, and what we'll feed down to routers, because routers are really good at this, is feed a filter list. And so in essence the box doing crypto understands the crypto and it automatically updates the filter list all the time. So you say in advance what you're going to do, you generate a rower, and the box has a filter list. It's kind of a just-in-case model, isn't it? That you have all this crypto material, foo, and you distribute it around the internet, magic, right? And then you load your routers with it, trust, and then the router has a filter just in case it sees an advertisement. That's the current framework inside ROAs and BGP-SEC. But it's not the only way of doing it. There are other approaches. Because when you look at something like TLS, SSH, what we use to go to a secure site, you know, when you go to HTTPS whatever, how is that security set up? The opening handshake of the secure session sends the certificates and credentials. Can we do that in BGP? Well, yeah. Because a BGP update, you can put other things as attributes, and oddly enough, you can actually pack the origination credentials right inside BGP itself. It is possible to do this differently, and instead of doing just in case, do just in time. Yes, then the router has an issue. It actually has to understand those origination credentials. It either puts it to a board, puts it to another server. It has to do things on the fly, but it's not building a filter. The update itself has materials that if you want to check it, you can. Different approach, not the one that's actually we're going down. So in the same way, there's problems and approaches with path validation. Because if you can secure origination, and you're an attacker, George, if you want to hijack my route, you just go, oh, I'm originating. No, actually, I'll attach Geoff. I will synthesize Geoff as the originator and then do the false path. Mission achieved, you're happy, I'm unhappy, you know, tears all the way through. So origination isn't enough, you've got to secure the path. So how do we do that? RPSL was one way of doing it. You say in a route registry what policies are, who I export, who I import, who's my neighbours, and you can construct filters. Realistically, complex filters from route registries never gained traction. It was an admission system, but it never was a transit system. So it's possible to do this, but the industry basically said, oh, too complicated, brains exploded. Interestingly, yes, I know, Cengiz was involved in this, and he understands the issues. Cisco came out with this about 10 odd years ago as sort of a poor man's version of securing AS adjacencies. And it said, you know, I won't secure the path, but I will certify and sign as AS3 that I'm connected to George, who's AS4. And George might well say, well, you know, that's true. I'll sign an attestation saying I'm connected to Geoff. And if everyone did that through adjacencies, then what you'd actually find is when you get a path, you can check if they're really neighbours. And if they're not really neighbours, that's a dud. Someone's asserting an adjacency that doesn't exist. So it's plausibility rather than proof. The last option is where they're going in CIDR, secure routing. This is the rocket ship to, I'm tempted to say Pluto, but I'll settle for Mars. This is tough. Every router needs certificates, every router needs crypto, every router signs every update. There's a fair deal of work involved here in complex signing. So there's a huge amount of technology flying around inside this. Bloat springs to mind because of the extraordinary amount of crypto to go one step further from plausible to actual. And you kind of wonder what the difference is in security terms and whether the additional price is worth the effort. Of course, the real thing is that last approach does not support partial use. I sign, you're not signing, everything gets dropped. So what you propagate is no longer of any good. In this issue, adjacencies, even if you're not playing, the rest of the path has adjacencies that one can check. So partial use kind of works better in that first approach than the second. And realistically, frankly, none of you are going to use secure routing all at once in my lifetime. Someone will always hang out. You're the guys running V4 and will do so forever too. You know, there's always going to be someone. So you have to think about this issue of partial deployment as well as full deployment. And quite frankly, if the partial deployment scenario is worse than the endpoint, we're in a really, really bad point. If the hill is so steep that even when you get there, it's good afterwards, this is not going to work. So, should we be using CAs and concentrations of trust? Are PKIs the right thing? Because quite frankly, it is one egg, it is one basket, it is an absolute point of vulnerability. But if you think about it, are the alternatives feasible or any better? Because if you have alternatives, I'll be one too. How do you know that you should have trusted me, even though I'm asserting I'm a very honourable person and I never lie about routing? Absolutely never. You know, so trust and hierarchies are difficult architecturally. Certification is difficult. It is complex crypto. There's a whole bunch of work being done by anomaly detectors where folk just listen and go, I've never heard that route from that AS, that's an anomaly, that must be bad. Or is anomaly detectors simply cheap veneer? It's just pantomime, they don't really detect effective attacks. So in some ways, there are other ways of doing it, but are they useful? And I'm not sure they are, unfortunately. So the last point, and I'm going to come down very quickly now, even if you secure routing, you haven't actually solved the billion-dollar problem. And I'm not sure I understand how to solve that problem. I am being given by routing an ostensible path to reach that destination. Is that true? If I send a packet into that path, will it really pop out the other end? And oddly enough, the routing system can't tell you that. The routing system is, if you will, propagating reachability, not the certainty of forwarding, because forwarding is in the opposite direction. So quite frankly, we're never going to be able to secure forwarding in this kind of architecture. So is it still worth trying to secure routing? It's an interesting question. I don't have clear answers, but I think in terms of architecture and design, these are questions you've honestly got to think about. Is partial deployment of any value? If I deploy security, will that help me? Is it worth my effort? Or do I have to rely on the rest of you to do it, in which case I'm stuffed? Because if I have to rely on you guys, I'm not going to do it. And you're not going to do it. Individually, if everyone's reliant on everyone, a common decision-making framework blows up in our face. Need I mention V6 again? Enough said. So we're in this kind of conundrum where, quite frankly, it's not even pick any two. It's good, or it's fast, or it's cheap. You can't get two. It doesn't work like that. So no matter how you cut it, you're going to get one and not the other two. So what's the compromise? Where do we actually try and do this? I have my own heretical view. And I must admit, it's not what the IETF is doing, and that's okay. I actually think RPKI is good. You know, that's actually the only thing I can see in technology that kind of fits. Who is awesome. Totally awesome, but complete crap, right? So RPKI is worth it. I actually think ROAs are really good too. I think ROAs kind of work. It's the right authority model. But I think path is an interesting problem. And I also think this whole issue of distributed CAs and everyone being a CA, too much trust, too many folk. I really think we should look at the RA model and try and reduce the number of points of trust. I think we'd all be happier. I think we should put stuff into updates and not be so sort of worried about altering BGP. Alternate distribution paths. How fast should we do this synchronization protocol? As fast as BGP. What's as fast as BGP? BGP. You know, why bother trying to invent something else? AS adjacency attributes seem to be a compromise that, to my mind, is good enough. Others may disagree, but to my mind, it's good enough. And because BGP never forgets, it's a TCP protocol, when I give you a cert, I never need to repeat it. The next time I should have given you the cert, I just send you a reference to the one I gave you earlier. So in some ways you can reduce the overhead by basically doing caching on either side because BGP never forgets. It's not perfect. Like all of these approaches, it's a set of design trade-offs. But the issue is where we are now is uncomfortable. We have a situation where the problem is acute and the solutions coming out of standards seem, to my mind, to err on the side of perfection when the merely good might have a chance of actually getting there. I've taken up enough of your time. It's almost afternoon tea. Thank you very much.
We'll take 2 questions for Geoff, if anyone has those.
I'm free.
Thank you, Geoff.
Thank you.
We'll break for tea. There is another session here in 20 minutes. You are most welcome. Thank you very much for coming.